Hello and welcome, H2 students taking your Prelim Paper 2 soon or A-levels at the end of the year. Here's something that we're going to learn from a 1-mark question on correlation and regression. So this question says that we want to study the correlation between the solubility of sugar and water. Temperature of water, sorry. So we have two variables, T and X, T being the temperature of water in degrees Celsius, X being the amount of sucrose in grams that can be dissolved in the water. So all is good. We collected 6 sets of data, and the only problem is one of the pieces of data is accidentally deleted. So if you look at the temperature, T equals to 60, right, the corresponding X value has been gone. So the good news is that somebody actually calculated the equation of regression before it was deleted. Right, the equation of regression is given at the end of this sentence. I can't really reach that far. Okay, we have to show that K is equals to 288. And I guess the immediate reaction for most students is that, hey, this is a 1-mark question. Let's just substitute T equals to 60. Right? Given this equation of regression, let's substitute T equals 60, X equals to K. So K should be 323. That should be our 1 mark. The only problem being that K is not 323, it is 288. So now most students will be panicking. Okay, you know what? Did I make a mistake? Did I copy down wrongly? Did I key into my calculator wrongly? Right? Turns out none of that happened. 323 is exactly what you get when you substitute T equals to 60. So what went wrong? Why should it be 288? Right? So if you think a bit more, you might realize what went wrong, and that is, let's take a look at an example of a scatter plot and a line of regression over here. Okay, so typically in a scatter plot, which is the bulk of our correlation and regression topic, you have experimental data that's in yellow, the yellow crosses, right? And then you have an orange line, which we call the equation of regression. That is usually calculated by a computer or software or your graphing calculator. Okay, so why do we have this orange line? That is because when you do an experiment, there's bound to be some errors. Human error, equipment error, measuring error, or just some random error. Maybe the wind is blowing, you know, this kind of things can happen, right? So if we believe our data to include errors, then perhaps we can actually find a line of best fit, and that should balance things out, and that will be our best guess of what our experiment is really trying to tell us, right? So that is the orange line. What happened in this question when you substitute T equals to 60 is you're substituting some value over here. You're trying to read off the regression line, and you think this is the value of your experimental data. It is not. The equation of regression line will never be able to give you back your experimental values. Yes? Yeah, substituting this value in, you will never get back this one. Okay, that is exactly what happened in this question. So what most students will do upon realizing this is say that, okay, let's assume K equals to 288. Let's fill out one list for T. Let's fill out one list for X. Use my graphing calculator, linear regression, A plus BX. Right? Let's chuck it in, and then I'll get this equation of regression line. Say that, oh, I got the same equation of regression line, assuming that K equals 288. So X must be 288. Right? So this is not the right way. Okay, what you're supposed to do actually is this question actually is testing you on the idea, the concept that the mean of the values of your variables will always be on the regression line, right? So over here I have a scatter plot of X and Y. That means X bar, Y bar will always be on the regression line. So for this question, for 1 mark, this is what you're supposed to do. You say that, okay, T bar and X bar must be on the regression line, and I can calculate what T bar is. I add 0 plus 20 plus 40 all the way to 100, then divide by 6, that is 50. Then I'm going to add up all the X values plus K and then divide by 6. Next, I'm going to substitute X bar, right, inside here, right, and T bar inside here, because this is the regression equation I'm given, right? X equals to 2.94857T plus this. Okay, so if you do that, you should be able to solve that K equals to 288, right? And that is the answer for this 1-mark question. But you can find this answer or solution online. There's nothing special about this. What's the point of this video? The point of video is if you have a healthy amount of skepticism, you should be asking yourself, why? Why should t bar x bar be on the line of regression? Right? If that did not come up to your head, let me maybe motivate the question a little bit, make you a bit more curious about what's happening. If this is your scatter plot of t and x, right? The blue ones are the actual values provided by the question, including k equals to 288, and t bar x bar is a point that's not near any of those blue points. Why should this be on your line of regression? Or maybe the better question to ask is, if this is a fixed point and I can change the gradient, right? That means to say I kind of have like a swivel, right? Just give me a while to fix this up. That means my line of regression is going to be just some line, right? I just need to change the gradient, right? It should swivel around the point t bar x bar. Does that feel weird? Right? If it does, then good, right? Like I said, you should always have a healthy amount of skepticism, right? And then we can get the line of best fit somehow by adjusting the gradient this way. Right? So in this video, I want to actually prove to you that x bar y bar should be on your line of regression. Okay, so let's deep dive a little bit and let's see why that should be true. So let's take a look at one of the experimental values over here, which I'm going to call x1, y1. Okay, so this yellow cross here is a certain value that I collected from experiment. Okay, so this is x1, this is y1. Okay, and following from what we learned from the question, if I substituted x1 into the line of regression, I will actually get this value, which is I'll call y prime 1. Right? Y prime 1 and y1 are not the same thing. But say if I wanted to, okay, let's just say that, let's write that down first. Our equation of regression will be a equals to ax plus b, for example. Okay. Then if I substitute x1, I'm going to get y prime 1 equals to a x1 plus b. Okay. So substituting x1 into this line of regression, I'm going to get y prime 1. So this is what I'm going to get. But let's say if I don't want y prime 1 over here, if I want it to be in terms of y1, what can I do? Then this is where we have the idea of an error, right? We call this E1. E1 is the error, right? The experimental error, right? That you're supposed to have, right? So I can take y prime 1 and minus away E1. That will give me y1. So I can say that y1, let me zoom out a little bit, y1 equals to y prime 1 and then minus E1. But I'm going to make E1 a negative value because then I can just write a plus. Plus E1. Okay. Then knowing that y prime 1 is equals to this whole thing over here, I can rewrite y1 equals to ax1 plus b plus some error term. Okay. So I have an equation in terms of y1 and x1. y1 actually is equals to my equation of regression, but with some adjustment error 1, E1. Okay, I can do the same for E2, y2 equals to some value of x2 substituted in, but that will give me y prime 2. Then I need to account for the error over here. Right, in this case, since the experimental data is above our regression line, E2 is positive. Right, and then there's E3 over here as well, and then E4, E5, and finally E6. Okay, so if I use this arrow to account for all these things, I can come up with 6 equations over here. Yeah, y1 and x1, y2, x2, all the way to y6 and x6. Okay, then the next thing is I'm going to add up all these 6 equations. Okay, on the left hand side, I'm going to get y1 plus y2 all the way to y6. Let me zoom out a little bit. So that's what I'm going to get on the left hand side. On the right hand side, if I add up all these ax1, ax2, I'll get a times bracket x1 plus x2 all the way to x6. I'm going to add up all these b's, that's just 6b. Right? Add up all these error terms. I ran out of space, so I use a summation sign, e1 plus e2 all the way to e6. Now here's the thing. If you use the method of least squares, right? Use the method of least squares to get this line of best fit. Then what we are guaranteed is that if I add up all these E1, E2, E3, if I add them all together, it will be 0. Right? Adding up all the error terms will be 0. That is how I know I got the line of best fit. That is how I know I've minimized the squares. Right? So if that happens, this will be 0. Okay. Then in the next step, I'm going to divide everything by 6. This one divided by 6 will just be this. This divided by 6 is this. This divided by 6 is this. 0 divided by 6 is still 0. Then what you realize is that this is y bar. This is x bar. Okay, and what we have is the equation of regression with the coordinates x bar, y bar substituted inside. So we have proven the x bar, y bar will always be on your line of regression, right? Regardless of whatever that you have. Okay, so yeah, this is something important that you need to remember, but maybe your notes don't really show why it's true. Okay, but knowing why it's true helps you to remember it a bit better. So I hope you found this helpful, right? And I guess I will see you next time, maybe in another interesting video. Until then, I guess I'll catch you on the flip flop.